Now we'll look at our last design example. Once again, we start at the same place. We can choose any pole and 0 that are going to satisfy this equation. So for this third design, let's choose a 0 equal to 1. Going through this more quickly, putting in the 1 for the 0, we find that that angle is a negative 117 degrees. Adding that to both sides, multiplying through by negative 1, then this expression has to be true. We can take the tangent to both sides and solve it for PC. So the pole has to be 2.65 if we choose a 0 equal to 1. When we put this 0 of 1 and this pole of 2.65 into our root locus or our g prime transfer function, we'll get the s plus 1 on the top from the 0, and we'll get the s plus 2.65 on the bottom from the pole that we're adding due to the controller. So now we can put this into MATLAB and see the root locus from this g prime. So putting design 3 into my choices here, I'm going to put the z of 1 and the p of 2.65 in, and we can make the new root locus for our third design. Right, now we'll use this to find the gain necessary for this controller. So again, looking for a desired pole location, -2 plus or minus 2j, getting as close as we can. So we're a little bit off here from just a rounding error. So for this purpose, I'm going to choose what I think is the closest one. We're very close to -2 plus or minus 2j, so I'll go with a gain of 5.3 for this system. And once again, I'll point out the overshoot it predicts is the same. It's a little bit different just because the pole's a little bit different, but it predicts an overshoot of 4.34 based on the baseline system with the poles at -2 plus or minus 2j. So if we put this gain with these zeros into our closed loop system, we're going to find here, again, dominant poles where we desire them, and we're going to have a 0 at -1 in addition, and a third pole at -0.667. Now, I'll point out at the moment something different about this design than the second design. Both the extra pole and the extra 0 are to the right of the real part of the dominant pole. So -2 is greater than the -1, 0 that we're adding and the -0.667 pole that we're adding. So we're going to simulate this, but we're going to see some strange things when that is the case. In the second design, we saw that the 0 and the pole were both to the left of the real part of the dominant poles. And in the first design, based on the 0 that we chose for our controller, we actually only had the 2 dominant poles and no extra 0 or extra pole. So going back into MATLAB and simulating, once again, we are using the exact same controller as before, just redefine the Z1 and P1 based on our analysis of adding our angles together, and then the K that we found by using the root locus. Right, so if I run this whole thing, this is what the response looks like. Notice we don't have an overshoot happening. This is not a true second order system, so we can't necessarily always expect it to look like one. Here we are really asymptotically approaching from the bottom the whole time, getting up to 5. We are driving the error to 0, but we are not getting an overshoot. Therefore, we don't have a peak time in this system. Our input effort is, the maximum is less. We'll find out what its value is in a second here. But it's not performing like the first 2 designs, and oftentimes we don't want our closed loop system to perform without that overshoot. Now, maybe this is a design we're interested in, so it's worth looking at, but probably we wouldn't go with this design. And this odd behavior that's different than what we saw before is due to that extra 0, that 0 and third pole actually being to the right of the real part of the dominant poles. Right, so looking here, we don't have a max overshoot, we don't have a peak time, so that 0 and 5 are just based on miscalculations here because we don't have a peak, but we do see that our maximum input effort is only 26.5 in this case. But based on the response, probably we won't go with this as the best design, but we'll compare them all as our next step.